We've been talking about addition of halogens, Cl2, Br2, I2 to Cc double bonds, which generally makes dihalides, vicinal dihalides. There's no problem doing this reaction to make vicinal dibromides or vicinal dichlorides, but iodine presents a problem because the products of addition of iodine across a double bond are unstable. That diiodide is unstable because the neighboring iodine can push out through neighboring group participation, can push out an iodide to regenerate the iodonium intermediate. So as long as there's that pathway for reversibility, you can't make a product that's thermodynamically unstable relative to the reactants. You have to obey thermodynamics. That doesn't mean you can't use addition of iodine across double bonds. You just can't isolate the diiodide. So I've shown you an example below that I would refer to as iodolactonization. That's the common term for this process. And let's go ahead and draw out. We typically don't go into great detail about stereochemistry in this class, but why do you get this particular stereoisomer? To help us understand that, I'm going to go ahead and draw out a nice looking chair, but we have to convert it into like a 5-membered ring transition state. Let me go ahead and start off by, maybe I'll color this in blue initially. Just going to do the best job I can to draw some sort of a chair-like transition state here. I'll use dash bonds at first and then I'll fill them in. So if I just draw out a chair like this, then I'll erase that extra carbon that I don't need. So that's my start of a chair. Let me fill in the key bonds that I need here, and then we'll try to recreate what's left over. So here's some of the atoms for my system. Now this is going to be a 5-membered ring, so let me erase some of this stuff over here that I don't need. Whoops, that's not my eraser. Let me erase some of this stuff that I don't need from my 5-membered ring so that I'll have a nice 5-membered ring transition state that really reflects anti-paraplanar relationships. That's always so critical. I'm going to go ahead and draw out this carbonyl group that's attacking. It's the carbonyl that's attacking. It is this atom right here that's the nucleophile, not the OH at the bottom. It's right. If you draw the lone pairs on the OH, they're donating into the carbonyl, making the carbonyl oxygen more reactive. Do not use this hydroxyl oxygen as your nucleophile. Maybe if you deprotonate that, you could, but this is not under basic conditions. So let me finish out drawing out this carboxylic acid functional group. There's that OH down there. And I've got this phenyl group at this position. There's an H going down. So if I drew this here correctly, I would have the H going down and that bulky phenyl group equatorial on this sort of chair-like transition state. Boy, that is the worst letter H I've ever drawn. There we go. So that's the phenyl group. And so now I have to worry about what this is going to look like when this lone pair of electrons on that carbonyl group attacks what will be the iodonium intermediate. There's going to be a 5-membered ring iodonium intermediate in this system. In order to explain the resulting stereochemistry, you'd have to draw an intermediate iodonium that looks like this, and then you'd have to do some sort of an attack. I think these I bonds would be behind the plane of the ring here. There would be an H atom over here, and so we would end up with some sort of ring opening of this iodonium intermediate. So no problem at making an iodonium intermediate. The problem is trying futilely to isolate, this would be the transition state, to isolate a diiodide. So this would be kind of a transition state. Maybe you could refer to that conformation as. So no problem making iodonium intermediates. The problem is trying to make vicinal diiodides. Okay, so addition of halogens. They go through these 3-membered ring. If you just have simple alkenes, they go through these 3-membered ring halonium ion intermediates. Let's go ahead and switch gears a little bit to something that does not go through a 3-membered ring intermediate. Yeah?
If we could go back to the last slide, my question is how far can that carbonyl be in order for that to happen? Like, does it have to be exactly 4 carbons away?
So the question is the question is how far away does the oxygen have to be from that electrophilic center? Of course, 5 atoms away is fantastic. You don't get much faster than that. It can be 6 atoms away. It can be, I'd have to look, probably 7 atoms away. The yield will decrease as you get farther and farther away. There will be other intermolecular reactions that start to compete once that oxygen atom gets further than 7. 8, I wouldn't give that any chance in the world because 8-membered rings have this internal transannular ring strain that prevents 8-membered ring formation from being efficient. But 5 is 5 and 6 would be common examples for halolactinization reactions. Okay, so let's talk about addition of electrophiles that don't make three-membered ring intermediates. Where you add to one carbon or the other is the way to think about it. And we have to think about which carbon do we want to add the electrophile to. So if we add mineral acids like hydrochloric acid, hydrobromic acid, hydroiodic acid, that wouldn't be very common. Maybe even sulfuric acid. The arrow pushing would look something like this. This shouldn't be any great challenge here. We're going to add a proton, but you can't tell from my arrow pushing which carbon am I going to add that proton to. My arrow pushing doesn't tell you whether I'm going to put the proton on the end or in that middle there. You have to wait for me patiently for me to draw this next intermediate. I think you probably already know where the proton is going to go. We're going to end up putting the proton on there so we get a more stable carbocation intermediate. And so this would be the product of that process. It would be the secondary carbocation. I'll draw the H, even though it's weird because there's two other H's on that carbon. That's the H we just added. So we make you'll prefer to protonate on this, let me go ahead and highlight it. You prefer to add the proton well, let me show where, what just happened. Boy, I don't know what I just did. Let me see if I can recover that. I didn't want to put the yellow there because that's where I'm forming the carbocation. I meant to put the yellow. Oh, it's not letting me. Okay. I prefer to put the yellow where I'm adding the proton. That's what I was trying to do. So you add the proton to this end carbon because that leaves behind the secondary carbocation. So you should have learned this in an introductory organic chemistry course. In the second step of HCl addition or HBr addition, we're going to add the halide anion back in. So it depends on whether which halogen we're using here. I'll just write the word nucleophile here. But that would be a bromide, a chloride, or an iodide would add back in. And that regiochemistry, where we add the nucleophile to the more substituted carbon over here, we refer to that as Markovnikov's rule. HCl tends to put the halide on the more substituted carbon. If you were adding water in, the water would go add to the more substituted carbon because you end up generating a more substituted carbocation when you protonate that CC double bond. Now, not all CC double bonds are equal, right? If I wanted to look up some procedure for HCl addition across a double bond, I might find a procedure where somebody takes a tri-substituted double bond and adds some sort of an acid to that or does a hydration to that. And I'd think, oh, that's easy. I'm sure I can do that on my alkene that looks like this. Not so fast. Right? Somebody else's alkene isn't the same as your alkene. You have to look very carefully at the substituents to understand the relative rates of reaction. I'm going to explain those relative rates of reaction here. I'm going to assign a relative rate constant. And these are all for addition of HX. So if you're just talking about addition of HCl or HBr, so HX addition across the double bond, let's assign just ethylene a relative rate constant of 1. Are substituted alkenes faster or slower to react? You put more groups on there, that's more sterically hindered. But you put more groups on there, the carbocation is going to be more stable. So which is it? Sterics, or the stability of the carbocation, or maybe to be more precise, or the nucleophilicity of the double bond? Let's see what happens when we put a single methyl group on there. Does that steric hindrance really slow down the reaction? Answer is no. It's 10 to the 7th faster. It is 10 million times faster to do this with propene. So would you rather generate a carbocation here that looks like this, like a primary carbocation, or would you rather generate a carbocation that looks like a secondary carbocation? You'd rather generate a secondary carbocation. The steric hindrance is not an issue here. What you care about is the nucleophilicity of that double bond. And putting an extra methyl group on the other side doesn't really change the fact that you're generating a secondary carbocation. So having that vicinally substituted double bond, both of these react at about the same rates. It's not a big difference here that's worth discussing. Now, if your substituent has double bonds in it, like this phenyl group, right? A phenyl group is a pi system, right? You can stabilize the resulting carbenium ion through resonance. And that's better than just having an alkyl group on there. So benzene rings are another 100 times faster than just a regular alkene. So let me go ahead and put a number here. That's about 10 to the 9th. So now we're talking 1 billion times faster than ethylene, right? The resulting carbocation should be much more stable. Look at what happens when we put both of the alkyl groups over here on the same carbon atom. Both of these groups over here are souping up the reactivity of this end carbon. They really make that more reactive. They're both good. You'll end up with a tertiary carbocation over here, and it's not the carbocation stability that determines the rate, it's the nucleophilicity of the double bond. But if we look over here at this geminally disubstituted double bond or the trisubstituted double bond, the steric hindrance of the trisubstituted doesn't make a big difference. These are now 1 trillion times faster. Let me draw this in red. 1 trillion times faster than ethylene. So if you're trying to find a procedure for halogenating your primary alkene, and you end up only finding a procedure for a trisubstituted alkene, that procedure may not work for you, right? That trisubstituted alkene reacts way, way faster and is way more nucleophilic than your lame terminal olefin that you're trying to. So look closely at alkenes because the substituents make a huge difference for the nucleophilicity of the CC double bond. Yes, question?
Yeah, on the primary alkene right there, or at least
This primary alkene?
the one next to it. I noticed that there's that squiggly line on the methyl group. I just wanted to know what that actually.
Oh, the question is, what does this squiggly line mean? It means it doesn't matter whether I'm talking about cis or trans, the rates are comparable. And in some cases, they are not comparable. So, but that's why I'm being careful in this case, to say that it doesn't matter whether it's cis or trans. Okay, so not all substituents are good. So here's an example where we've got 2 olefins down here in this bottom example. I've got one here, that's like that geminally substituted case. And over here I have something that looks like a trisubstituted olefin. But it's not just a regular trisubstituted olefin on this side. Right? I can tell you what the product of this reaction is going to be. The product is going to be protonation here. On this, whoops, let me do that in my marvelous red color here. So the product of this, if I add HCl to this double bond, the product is going to be addition to this external disubstituted olefin, not the trisubstituted olefin. And you'll end up generating a nice tertiary carbocation intermediate. Should look very comfortable. And the end product of this process is the chloride will attack that, and you'll end up generating this tertiary alkyl chloride. And you don't have to worry at all about it touching that trisubstituted olefin. Right? The issue here is that this other group on here is not just a regular alkyl group. That carbonyl will destabilize any carbocation at that center down there. So you don't want to make a carbocation at this center. So I'll just say no R+, because the carbonyl would massively destabilize that carbocation. Right? There's a huge difference. I don't know what the rate constant is for addition to this enone system, but enones are not good for adding electrophiles. That's tough. It's not as easy. So you'll get it's very easy to get selectivity in addition to olefins if you just look at these relative rates. All right, let's take a look at a different type of electrophile. Maybe actually it's not that different. We've already talked about this type of electrophile, but it's going to seem mysterious once we draw out the Lewis structure. You should have already covered in an introductory organic chemistry course epoxidation of CC double bonds to make epoxides. By far, the most common reagent that is introduced to you is metachloroperoxybenzoic acid, MCPBA. And when I look at MCPBA, everything about this is just screaming to me that it has this weak OO bond there that is going to break, that is guaranteed to break. That bond is weak, boy. And in nature, you want to trade that weak OO bond for anything else other than that weak OO bond. Somewhere in the reaction, that bond's going to break. Peroxides are explosive, peroxides are reactive, and so that's what drives the reaction. Let me go ahead and draw out the product of this. You can see that there's 2 double bonds in this starting material. I was very careful to pick an example where there was a disubstituted olefin and a trisubstituted olefin. Now, based on what I told you before on the previous slide, you should expect that the trisubstituted olefin should be more nucleophilic. Let's go ahead and see what the product would look like. If that were your guess would be exactly right, because you can very, in high yield, selectively epoxidize the trisubstituted olefin and not end up with any of that epoxide on the disubstituted olefin. So that's the product of the reaction. It's the more reactive trisubstituted double bond that reacts faster. All CC double bonds are not equal. Now, I'm going to show you how we're going to draw the arrow pushing mechanism for this in this class. It would freak you out. I don't even know if we show the mechanism for this in introductory organic chemistry courses. Now we're going to acknowledge the fact, when we draw out the mechanism, that this lone pair over here is 5 atoms away from that H on the peroxy acid. You can't stop it from hydrogen bonding. You can't stop that H from interacting with the carbonyl. It's happening. And so I'm just going to go ahead and start off my mechanism by drawing a tautomer, where we have simply transferred this proton from the OH to the carbonyl H. And I'm going to draw a an alternative tautomeric form for this peroxy acid. Boy, that O plus doesn't look so good, does it? And look at that OO bond. It's weak, it's going to break, but I end up putting a negative charge on that end oxygen. And the thing that is going to freak you out is we're going to use the CC double bond to attack that O minus. The CC bond is the nucleophile, not the O. The CC double bond is the nucleophile. We're going to use this CC double bond to attack and break that O and attack that O bond. And you might think, well, why would I want to attack there? It's got a negative charge. Here's why you want to attack there, because we're going to take these electrons and push them into that O plus carbonyl. That's why you attack the O minus. And you can't do that. You can't push the electrons to the O plus if you attack this other oxygen on top. So now the closer and closer that this oxygen here gets to that double bond, right, you're not going to generate any carbocation intermediate, but the closer this O minus gets to that double bond, the more the lone pairs on the O are going to attack any carbocation as it forms. We don't generate carbocation intermediates in this reaction. It is just like the addition of Br2. It is just like the addition of Cl2. The only difference is we've got this crazy looking, instead of having a Br leaving group, we've just got this crazy looking, it's not crazy looking, it's a carboxylic acid is the leaving group. So you have that crazy looking leaving group. It's just like the arrow pushing for addition to Br2 or Cl2 or I2 or bleach or any weak bond. You just have to get over this O minus. If you can get over that, attacking the O that has the minus, then you'll be in good shape, right? This is very similar. Let me go ahead and draw out it's just like this arrow pushing. Here we go. And then there's a lone pair here that comes in and attacks. So there's no carbocation intermediates. Well, if there's no carbocation intermediates, how do we rationalize the relative reactivity? It's kind of a similar relative reactivity that we saw for reactions that generate carbocations, but it's not exactly the same. I'm going to show you the relative rates here for epoxidation with MCPBA. So over here, if we look at the rates of epoxidation with MCPBA, once again, I'm going to assign just a simple CC double bond, ethylene, a relative rate constant of 1. Right? Are things faster or slower than ethylene? How do the substituents affect that? Is there some steric effect that slows down epoxidation? If I come over here and I put 2 methyl groups on that alkene, does it get slower or faster? Well, it's faster. It's not 10 to the 7 faster, but it's faster. You would have no problem substituting butene in the presence of ethylene. It's 50 times faster. Now, if you put a benzene ring or some sort of double bond system, let me draw out, I wish I had drawn that out, right? There's all these pi electrons in this benzene ring that are donating in to this olefin, right? There's all this donation that's occurring where these pi electrons are donating in and making a new orbital that's more nucleophilic. So conjugated double bonds will react faster. Not 100 billion times faster, but faster. And so let me go ahead and give you a number for that. So this substituted styrene is an alkene with a phenyl group on it. That's 240 times faster. 240 times faster than ethylene. And if I go to a tri-substituted olefin, again, that is now more nucleophilic. Now, again, enones, that carbonyl group lowers the energy of the pi electrons. The pi electrons in that enone double bond are less reactive, and I unfortunately don't have a number for you. I'm just going to tell you it's way, way less than 1. If you use MCPBA to epoxidize any of these olefins, you could easily do that in the presence of an enone. It would be very slow to epoxidize. Not impossible, but slower. Now, let me just remind you, why is this faster? It's not 10 to the 12th faster, right? But it's still faster. Why are alkenes reacting more quickly? It doesn't go through a carbocation. You can't use your carbocation rationale to explain this. It's because these CH bonds, just like for the HCl addition, those CH bonds are donating into the pi system. There's donation. I don't want to draw that arrow because I don't want to, and all those CH bonds, all of them, those bonds that are adjacent to the double bond are donating into pi, making a new orbital that's more nucleophilic. So it creates a new pi-like orbital that is more nucleophilic, and the more of those bonds you've got, the more nucleophilic. In this case, you're also adding steric hindrance, but usually the sterics is not as important as the electronics. The case holds here. Tri-substituted olefins are more reactive than di-substituted olefins. So the rate acceleration is not exactly the same as the HCl addition, but that's a pretty bankable observation there. Tri-substituted is better than di-substituted, and that's going to be better than mono-substituted olefins. Yes, question?
For the di-substituted, like the middle one?
Yep.
Does it matter if it's cis or trans?
The question is, what's the relative rate of epoxidation for the cis versus the trans? And I don't remember that number, I'm sorry. And it was probably in this review. Comparable. I'm going to guess that the cis was a little more reactive, but not enough for you to selectively epoxidize the cis in the presence of the trans. I would guess you wouldn't get good enough selectivity, right? You need, if you want to have reactions that are useful, you want one thing to be 10 times more reactive than the other. Factor of 10 is what you need. Yeah.
So I remember at the beginning of class you said only 3 arrows, but I noticed the problem with this is that I feel like I have to draw 4 arrows.
If I ask you, in order to follow my rules, then you should draw this. You should draw it like this. Here's the way. So the question was, how are we supposed to follow your stupid 3-arrow rule if I've drawn 3 arrows? Here's how I'm going to ask you to do it. Let me come back and erase these arrows. And that's a good question. So let's do this. Let's draw a different. Let's draw a different arrow pushing for that first step in order to obey the 3-arrow rule. So let's draw that protonation like this, and then we'll use the pi electrons to grab that. And so then when we draw this structure here, it looks like this. Oh, I got that positive charge in the wrong place. There will always be some way to obey the 3-arrow rule, and sometimes you have to draw an extra resonance structure to get there. And so now when I get to this different depiction of that same molecule, we'll have 3 arrows in there. And maybe this is a better depiction, I don't know. But at least it obeys the 3-arrow rule. Okay, so again, these addition of Br2, addition of Cl2, epoxidation, those don't go through carbocation intermediates, but we still see this trend that tri-substituted double bonds are substantially more reactive than di-substituted or mono-substituted double bonds. All right, the last electrophile that we're going to talk about that is not a carbon electrophile is hydroboration, because it's typically covered in sophomore organic chemistry courses. And I just want to sit here and marvel at this electrophile, borane. Man, that is a screaming hot electrophile. My gosh, it's like a methyl carbocation. It's like a methyl carbenium ion, right? The boron wants 8 electrons. You come over to the periodic table, boron wants 8 electrons, just like carbon. It is as reactive as a methyl carbocation, as a methyl carbenium ion, because it wants 8 electrons. So when you think about this, everything about me wants to take these electrons in the pi bond and add them to that boron. So it gets, now that's not great, it's not perfect, but you generate another system that only has 6 electrons, but at least it's tertiary. And if we draw out this intermediate, it would look like this. Okay, but you know what? And that would exactly explain the fact that process right there would exactly explain the fact that we have a boron-carbon bond attached right here. Right? We don't add the boron to the more substituted center. That's chloride adds to the less substituted, to the more substituted center. So normally if you were adding chloride, making bonds to chlorine, or making bonds to bromine, or making bonds to water, you would add all those heteroatoms to the more substituted carbon. And in this case, hydroboration, we add the boron atom to the less substituted carbon of the double bond. Now, this is not the right mechanism. There is no carbocation intermediate when you do hydroboration. It's a concerted process just like the epoxidation. Let's finish this up. because as this boron gets closer and closer and closer to that double bond, as you start to generate this hydridoborate, those hydrogen boron bonds become nucleophilic. The bonds, the hydrogen boron bonds are absolutely not nucleophilic in this species. There is no way that BH3 is going to donate a hydrido group to anything. But once you change that to B minus, in the transition state, as you're changing that to B minus, these electrons start to come back in and add at the same time. You don't generate this intermediate here. It's not, so let me just write no intermediate. There's no intermediate like this. But this intermediate may help you if you're trying to rationalize the regiochemistry. So there's no intermediate that looks like this in a hydroboration. Let's go ahead and draw out the next thing that you get in hydroboration. The next thing that you would get would have the boron either on the top or the bottom face. You'd get equal amounts. And the H would be on the same face as the boron. So it's a syn addition. H and the boron add from the same face because right, the hydrido group has to add while the boron is adding. So you get syn addition. And because there's two more BHs on here, suddenly the mechanism that looks so clean and easy just becomes kind of complex because we have to do this 2 more times. I'll just write 2x there. We have to do that 2 more times on 2 other groups. So if you're using BH3 as your hydroborating reagent, everything just becomes 3 times as your mechanisms become painfully 3 times longer for no real benefit. Now, nobody wants a carbon-boron bond in their molecule. That's not really what, they're sensitive to molecular oxygen. There's all kinds of issues with that. And so everybody converts these carbon-boron bonds into carbon-oxygen bonds, like the one over here. And the way we do that is using hydroperoxide anion. And we don't buy solutions of sodium hydroperoxide. You dump together hydrogen peroxide, just like the bottle you buy at the grocery store, and sodium hydroxide, and you make your own sodium hydroperoxide. So really, we could write it like this, NaOOH if you wanted to, but everybody just dumps those 2 chemicals together and makes sodium hydroperoxide. Let's look at the mechanism for how you convert a carbon-boron bond, right? A carbon-boron bond like this one over here that I've highlighted in yellow, how do you convert that stereospecifically, with retention of stereochemistry, into a carbon-oxygen bond, which is quite useful. So we're going to draw out the mechanism with hydroperoxide, and it's going to turn out to look a lot like a Baeyer-Villiger oxidation that we might have seen before. So it's going to be a migratory displacement. We've seen migratory displacements before, right? There's some bond that gets weakened, and it migrates over and pushes out some leaving group. It's the same deal here. Let's go ahead and walk through that. Now here we are with this boron, once again, with 6 crummy electrons here in this boron compound. So doesn't it feel like you want to do this? 6 electrons. Now we got 8 electrons. We're going to have 8 electrons in this next intermediate. So let's go ahead and draw that out. I'm not changing the stereochemistry on that carbon up above. That's still the same. Now I'm going to be very careful here about how I draw this oxygen-oxygen system. I'm going to draw it like this. I'm so clever because I've done this mechanism many times. I know to make this bond antiperiplanar to that weak, lame oxygen-oxygen bond. Look at this weak bond here. You know you're going to break that bond. So let's put this carbon-boron bond anti to it, antiperiplanar. Let's draw it like that. That way it makes sense. Everything will make sense when we draw it like that. And it can rotate all over the place, but when it rotates into this particular conformation, now when you add the hydroperoxide to the boron, it's not just regular boron anymore. Now it's a boronate. Boronate. Negative charge. Boronate. That means all the bonds to boron are nucleophilic. So we got this nucleophilic carbon-boron bond, antiperiplanar to this weak oxygen-oxygen bond, and you just can't stop this migratory displacement. And maybe you're not comfortable making hydroxide act as a leaving group. Yeah, that's no good for SN2 reactions. This isn't an SN2 reaction. Let's go and draw the next intermediate. The next intermediate is a boron ester. I've still got this O here. That OH acted as a leaving group. It's down here on the bottom. And now we've got this alkyl group attached to that oxygen atom. And it will preserve the stereochemistry, any stereochemistry that we had at this starting. The configuration whoa, what did I do? The configuration, I was going to say it's preserved, but it looked like I erased it. The configuration of this, at this carbon center is retained, right? If you had an R stereogenic center, it would stay R. For some reason, I got an extra methyl group on my, let me try to fix that. So the configuration would be preserved. And then you just do more boron ester exchanges to finally get to your final product. I'm not going to show the protonation steps here. Protonation steps are not interesting here in this system. How do we get rid of this thing? Maybe I'll show the first step. There's hydroxide there. There's that boron that really wants to have 6 electrons. No problem adding the hydroxide in. You'll generate an intermediate here. Right? This has to occur 3 times to replace all those R groups on the boron, and I'm only going to show this process for one of these carbon-boron bonds. So you'll generate this new boronate intermediate, R, OH, and minus. And then we'll push out one of these two oxygen groups. I'm not going to show pushing out hydroxide. That just takes us backwards. I'm going to show making this act as the leaving group. So you push out your alkoxide, and then it protonates. Don't have room to show that. Don't have room to show the addition of this proton over here, but you get the idea. Okay, so hydroboration-oxidation kind of seems to me like the most interesting part of that is the oxidation. Not even, seems more interesting to me than the hydroboration part, with all that migratory displacement and antiparaplanar relationships and weak bonds. All right, so we've been talking about addition of electrophiles to CC double bonds. But, you know, maybe it's cool to form bonds to chlorine or bromine. Maybe it's cool to form bonds to oxygen or boron. But you know what I really care about, because I'm an organic chemist? I care about making carbon-carbon bonds. And so let's really focus on how do you make carbon-carbon bonds using CC double bonds as nucleophiles. So it's kind of the same, you know, all those orders of reactivity that we talked about for how nucleophilic is a tri-substituted double bond versus a monosubstituted are going to apply here. So in this section, we're going to take a look at the addition of CC double bonds to carbenium ions, to more carbenium ions, and what can we do to amp up the nucleophilicity of this double bond? It'll be the same tricks that we've been using before. You put carbon-silicon bonds, allylic, or you try to use some trick to have some sort of a nucleophilic bond next door that amps up the nucleophilicity of this CC double bond. Now, this is not easy. Making carbon-carbon double bonds doesn't seem that easy. Nature has no problem doing this. Let's take a look at how nature does it. So in your body right now, you've got this molecule floating around called oxidosqualene. Here's the structure. Look at all those double bonds in there. They're not disubstitute, they're tri-substituted double bonds. Doesn't get more reactive than that. When nature fiddles around with double bonds, it goes right to the good stuff. Tri-substituted to get all that nucleophilicity. And so nature is taking this molecule called squalene and converted it into the epoxide without using MCPBA. Nature has no problem doing that. And so it's got this strained epoxide in here. And there's an enzyme in your body called lanosterol synthase that positions a group in the active site of the enzyme, an acidic group right next to that epoxide. And it's going to protonate that epoxide and turning it into a reactive epoxide intermediate. So here in the active site of the enzyme, right, we've got some sort of protonated epoxide, and that wants to open up. And in fact, inside that enzyme active site, this oxidosqualene folds up into a very particular shape. It can't fit in the active site unless it folds up into this very particular shape. And when it folds up into this particular shape, the epoxide is next to the acid, and this carbon double bond right here is positioned right next to that tertiary center. Right? This thing wants to open up to give a tertiary carbocation, and as it does, you know, it's not just that it's getting opened up, it's that this double bond right here is pushing it open. Like this. Helping to break that carbon-oxygen bond. Marvelously designed to fit in the active site so that that double bond is ready to push out that carbon-oxygen leaving group. Now, you don't just leave a carbocation here alone. There's another double bond positioned and ready to attack. And that would normally leave another tertiary carbocation over here. But of course, in the active site, this other double bond over here is perfectly positioned to attack. And that would leave another tertiary carbocation. Well, actually, that would leave a secondary carbocation over here. But that's positioned with another group ready to attack. All of these things are happening in the active site with perfect control of stereochemistry. And so the first intermediate that gets generated is this tertiary carbocation. People have even named it. It's such a famous carbocation. This is the protosterol cation here. There's a carbenium ion right there. And it doesn't stop there. Because as long as this protosterol cation has this conformation in the active site, it is held in a conformation where this hydrido group right here is aligned with the empty p orbital. It is aligned to migrate over into that empty p orbital. And this H, this CH bond on the bottom, I didn't draw it in the best way to show that, is aligned at this, either sequentially or at the same time. It's hard to know that sequentiality there to migrate so you don't leave a tertiary carbocation there. And this methyl group right here is perfectly aligned to migrate at the same time so that you don't leave behind a tertiary carbocation. And there's one more shift that occurs right here. It's the shift that occurs right here that allows this methyl group to migrate over. All these migrations are occurring in the active site of this enzyme with perfect control of stereochemistry. And the enzyme in the active site has this basic group, oxygen with a lone pair, that simultaneously, or not simultaneously, you don't know the order of events, it pulls off that proton and leaves this double bond in the middle. So you get this tetracyclic structure. This has a classical steroid ring system, and they're commonly numbered. If you tell somebody I'm synthesizing something by making an alcohol on the C ring of a steroid, you know they're talking about that third ring there. Everybody understands, you should understand what is an ABCD ring system of a steroid. So this is what your body does. It makes lanosterol that is the most worthless and pointless molecule in the universe. There is no use for lanosterol in the human body. What happens is your body knows this one trick. It's a one-trick pony. It makes this one steroid that it has no use for, and then it spends step after step after step after enzyme after enzyme after step to convert that useless compound into all the important human steroids. Cholesterol for your cell membranes, estradiol signaling molecule, testosterone, progesterone, cortisol, all the super potent biologically active steroids in the human body come from this worthless piece of junk. It's easy to be amazed by biology. It's like, wow, it made like 4 rings and I don't know how many, 8, 9, 10 stereogenic centers all perfectly. Well, maybe it wasn't so perfect. If it was perfect, it would have directly made all of these, not something it didn't need. But okay, so that's the one-trick pony. Boy, if we could do that, even that, if we could do that, we'd be pretty amazing. It's pretty amazing what biology, what an enzyme can do by holding things together in a certain conformation. Okay, so if we wanted to make carbon-carbon bonds by adding electrophiles to CC double bonds, how would we do that? We've been doing this for a long time. Chemists have been doing this for a long time. These reactions date back to the 1800s. People have been making CC bonds by adding things to double bonds. And I'm going to show you the prototypical example of this type is called the Prinz reaction. So in the Prinz reaction, you take some sort of a carbonyl type compound. That's not electrophilic enough. Boy, formaldehyde is electrophilic. It's still not electrophilic enough. And under acidic conditions, you can protonate that carbonyl or generate something like an oxonium ion. Let me go ahead and draw out that intermediate. I don't think I need to show the arrow pushing mechanism for protonation of a carbonyl. I hope I don't need to show you that anymore. So you're going to have this oxonium ion floating around, and in this original Prinz reaction from the 1800s, when you have this protonated formaldehyde floating around in the presence of isobutylene, you get CC bond formation. And the result would be, if you follow my arrow pushing, the result's going to be a tertiary carbocation, which sounds pretty great. There's our new CC bond right there. Wow, that's great. That's awesome. Now, you can't isolate that, right? So what do? You rely on the fact that there's still water present in the reaction mixture. And the problem is, you can't really control what the water does. So one of the things that the water molecule does is that the water molecule can deprotonate next to the carbocation to generate the CC double bond. right? That would be the completion of an E1 elimination mechanism. That's E1. And that's one of the products that you get. But that's not the only product that you get out of this Prinz reaction. Looks like a great reaction, right? Except you get two products. Nobody wants two products, ever. You want to make one product, and you cannot stop, I'll draw it in blue, the arrow pushing in blue this time, you can't stop some of those water molecules from adding into the carbocation, and that goes through an SN1. That's an SN1 type mechanism. So you get both the products of E1 and SN1. That's pretty typical. Like usually when you're trying to do carbocation chemistry, you'll get mixtures of those two. So that's not really a useful process. So the reaction kind of sat around for a while. Not many people were using that reaction. Can't think of many people, but like if you wanted to make this a useful reaction, right, what do you need to do? Not everything is as reactive as formaldehyde. Formaldehyde has crazy reactivity. Well, you want to soup up the reactivity of your alkene somehow. And so how can we do that? Well, let's go ahead and take a look at how some of our famous tricks here work in souping up the reactivity of the alkene. That isobutylene, that dimethyl substituted alkene there, I'm going to give that, I'll assign that a relative rate constant of 12 here. I don't know why I didn't do it relative to 1. And we're going to see what happens if we put this long carbon-silicon bond at the allylic position. We already know what that's going to do. That carbon-silicon bond is going to be donating into the pi system. That creates a new pi-like orbital that's more nucleophilic. And it specifically makes it more nucleophilic at the same position it was already nucleophilic at the end. It'll specifically soup up the rates of reaction. The rates at which electrophiles add to the end of that alkene will be faster. How much faster is it? Well, a lot faster. Man, if I had a choice between which type of alkene to use, just a regular alkene or an allosilane, I'd go with the allosilane. Right? Would you rather spend 1 day in the lab or be done 16,000 times faster? That's like ChatGPT for molecules. That carbon-silicon bond just accelerates stuff. And if you want to go even faster, make a longer bond, go to tin. How much faster is that? I'm going to run out of room here. It's 45 million times faster. Boy, I wish I could do my work 45 million times faster. I'd be done. If we come over here to, actually, I've got that wrong. Sorry, that's totally wrong. It's only 4 million times, 4.5 million times faster. Okay, sorry to oversell that. 4,500,000. Now, you couldn't know this. There's no way for you to know what would happen. But let's suppose we go back to that boron case. Remember that boron, the boronate intermediate that we had in that hydroboration-oxidation? That's not a long bond. That's the same length as a CC bond. But there's a negative charge on boron. It's a boronate, 8. That tells you all the bonds to boron are nucleophilic. So if you take a regular length bond that is now negatively charged, that boronate, it turns out you could never have guessed this, but that combination of a regular length bond but negatively charged makes that even more reactive than the tin system. That's 15 million times more reactive. Wow. Man, alloboronates, that sounds like the stuff. Now, it may seem like a big hassle to put these extra groups on there because I don't want to put tin on my molecules. I don't want to put silicon on my, right? If you're trying to make these kinds of products, like if your goal, and this is typically the goal, if you're trying to make products that look like this up here, that just have a new CC bond right here, you don't want all that extra tin and silicon and boron stuff on there. But you know what? That's not going to stay on there. Because when you go through these mechanisms of silicon or boron, the silicon and the boron and the tin don't stay. You end up pushing those groups out to make alkenes just like this. You would never know that that silicon or that tin was there because they disappear in the end. And they completely control the regiochemistry and you don't get any addition to this carbocation. So if you want to make systems that look like this, start with one of those long bonds here to tin, to silicon, to boron, and it'll disappear in the end. And you'll have the double bond exactly, you'll know exactly where that double bond is going to be because it's going to be created by this loss of this siliconate or boronate or stannate species. So you get control over where the double bond ends up. You know where it's going to end up in the end, and you don't get this annoying addition to the carbenium ion. So real advantages to using allosilanes, allostannanes, alloboronates when you want to add electrophiles. And the electrophile we want to add is carbon electrophiles because we're organic chemists. We want to make CC bonds. Let's take a look at how you might rig up a system so it could do this Prinz reaction. But instead of using just a regular alkene, look at this, we're going to use an allylsilane on there. And so here's a mixed acetal that somebody made, and they're not treating it with a regular protic acid, they're treating it with trimethylsilotriflate. And trimethylsilo loves oxygen. TMS loves oxygen. It just does not love this oxygen on the triflate. Right? That triflate thing does not want to share. Let's just draw out that triflate. Here's the triflate. That oxygen there is a sucky oxygen. Once that comes off, once this group comes off, the triflate is just going to float around and not do anything. So yes, silicon loves oxygen. It just doesn't like that triflate oxygen. So this TMS triflate is going to silylate. It'll silylate here, and then the silicon will pop off. It'll silylate here, and then the silicon will pop off. It'll silylate here, and then the silicon will pop off. It'll silylate here. Eventually, once you put that silicon over here, and then make this carbon-silicon bond, you're set up to push out that leaving group. And I've already got the arrow pushing there. You're set up to have these lone pairs here push out the leaving group here. And there's a contribution in this case from the benzene ring. It's kind of like a benzylic carbocation, if you want to think about it that way. But the main pusher here is the lone pairs on this other oxygen. And so that generates an oxocarbenium ion. It looks kind of like a protonated carbonyl. When you look at it right here, it looks kind of like that formaldehyde thing. And they've designed this system so it's 5 atoms away from that allylsilane carbon. Where is allylsilane nucleophilic? The allylsilane is nucleophilic right here, right? That carbon-silicon bond is amping up the nucleophilicity of that carbon. So you don't get much better than this. I mean, you're set up so that this carbon-carbon bond is positioning the nucleophilic carbon atom 5 atoms away from that oxonium carbonyl carbon. So you get this rapid 5-membered ring formation that leaves behind, what does it leave behind? It leaves behind a beta-silocarbocation. And we know what beta-silocarbocations do. They don't just stick around. So now you have some sort of a nucleophile floating around. What's that nucleophile? I don't know. It's one of a couple of things. It could be another substrate coming along with its lone pair and picking up that silicon. It could be the triflate just temporarily picking it up and regenerating the catalyst. You don't know which substituent is attacking here, right? It could be just another substrate molecule, and I'm not going to draw that. I'm just going to write Nu to indicate that some, almost always oxygen loves silicon, is going to add in, make a siliconate intermediate, 5 bonds to silicon, negative charge. The bonds to silicon are nucleophilic. And so now this will just push out that leaving group, or at least the silicon-carbon bond will bend over and give the electrons to the carbenium ion. And that's what leads to the product here. So you don't have to worry about, do you get the final double bond here or the final double bond here? You know your final double bond is going to be right where that silicon was, because that's going to be the collapse of this beta-silocarbocation. Okay, this has been used over and over and over again to make carbon-carbon bonds and complex structures. Right? Once people figured this trick out of, allylsilanes and allostanines, they took every single carbocation species in the universe and added them to these to make rings, to make acyclic structures. Let's take a look at a slightly different variation of the same reaction. They're just switching it up a little bit. And so what they're doing is they're taking advantage of the fact that you can make your own. Instead of starting with a mixed acetal that you had to synthesize and isolate and purify, they just took an alcohol and threw in an aldehyde and said, well, maybe we'll have a little bit of an hemiacetal intermediate. And maybe that'll be good enough. So in this mechanism, you would protonate the carbonyl. There's trifluoroacetic acid. That's not triflic acid. It's trifluoroacetic acid in there. It would protonate the carbonyl. And that would allow you to start forming acetals and hemiacetals. I'm not attacking the positive charge. I'm attacking pushing the electrons to oxygen. So I'm not going to show the whole mechanism for formation of this oxonium ion intermediate. There's several steps there. If you're not familiar with that, practice that. But now we're right back to that thing that looks just like formaldehyde. Right? You really want to attack that carbonyl, super reactive. And that makes this 6-membered ring through this kind of process we showed above. Okay, when we come back, we're going to see a lot more examples. Maybe not a lot more examples. We're going to see more of the same thing over and over. Allosylanes, allostannanes, alloboronates attacking carbenium ions or oxonium ions that are electrophilic on carbon. Same thing over and over.